So hello and and good day on this beautiful afternoon. So today we will continue with our Igneous and Metamorphic Petrology class. I will record today all the 3 hours for this week. That means I will make a 2.5 hour session. So we have now 5 weeks left till the end of the semester. That means we have 15 hours of class left and we are in good time. So we are in the time frame. We will have in December an excursion. I have to check where we can go, maybe to the Lüderitz area or something like that. And we will have a microscopical practica also after the examination. So I have handed out you yesterday or 2 days ago the test number 2 and number 3. Yeah? One with a lot of questions regarding to Igneous petrology, one with a lot of questions to the metamorphic petrology as far as we have done it by now, when I have shown you, at the beginning, an introduction in Igneous petrology and metamorphic petrology. This is all covered by that question papers. So, and then at the end of the semester, I will hand out to you a second question or another test. And this test contains then or have question from the first part of the semester as well as of the second part of the semester. And when you are going through these questions from the second test, you should be easily easily task for you to pass the examination. So, but now we are continuing just with our class on Igneous and metamorphic petrology. So, introduction to igneous rocks, part number 2. We have already done part number 1. So, and now we are continuing. I have again a lot of diagrams. A lot of diagrams maybe you know from before, like these ones. Here we have triangle diagrams. Triangle diagrams means we have diagrams in the ternary system. Here on the upper left side we have a triangle diagram with the end members here at the corners: olivine, orthopyroxene, clinopyroxene. Then you know already by now from your third year class we are talking about ultramafic rocks on that diagram. If our rock contains more than 90% of olivine, we are talking about the dunite. If it consists mainly of olivine and orthopyroxene, we are talking about an harzburgite. Whereas if our rock sample contains mainly olivine and clinopyroxene, we are talking about the wehrlite. Or at lower olivine concentration, we are talking about the olivine clinopyroxenite. And on the other hand, if we are replacing the clinopyroxene with the orthopyroxene, we are forming there orthopyroxenites when we have a lot of orthopyroxene inside the system. If we have a rock containing mainly orthopyroxene and clinopyroxene, we have a websterite. If we are adding some olivine, then we have an olivine websterite. So, and in the upper part of the triangle we have the lersolite, and this dark field shows us the main composition from all these mantle rocks, where they are chemically at home. Yes, we have here mainly lersolites, and these lersolites we can then subdivide into plagioclase lersolites, in spinel lersolites, and in garnet lersolites, and that is a pressure depending thing. Going to the right side, on the right upper hand side, we have the triangle for the gabbros. You know, a gabbro that is also an intermediate rock, not an ultramafic rock, it's an intermediate rock. But it can also be a mafic rock, depends on the silica concentration inside. Here we have the three end members. We have the plagioclase on the top. If we have more than 90% of plagioclase inside our rock, we are talking about an anorthosite. So then we have, if the rock consists mainly of plagioclase and clinopyroxene, we have a gabbro. Whereas if the rock contains mainly plagioclase and olivine, we are talking about troglodytes. So, and here in the field between all of them on the upper part, we have the olivine gabbro and the black field here. That shows us the composition of the most sampled gabbros from the oceanic crust. Yeah. So, and the gabbro is chemically the same as an basalt. So, and if you are looking at the diagram number C, we have then more detailed lower part of different gabbros. Just we have at one corner then the orthopyroxene and the clinopyroxene instead of the olivine, but at the top we have also the plagioclase. So then we can form a norite, yeah, if the rock contains mainly plagioclase and orthopyroxene. And if the rock contains mainly plagioclase and clinopyroxene, as at the diagram under number B shown, we are talking about the gabbro, and between we are forming the gabbro norites. So, and that is the classification of the mafic and the ultramafic rocks. So, and we are using always classification diagrams to figure out from the geochemistry what rock type we are talking about or dealing with. So in this diagram you know as well that is the QAPF diagram, which is then used for the igneous silica, for the igneous plutonic rocks. So we have here on the upper part of our triangle, we have again our granitoid rocks, yeah, and on the lower part of the triangle we have the silica undersaturated rocks, and then the upper part the silica saturated rocks. So, and then we have here the different fields depending on the composition. In the upper part between quartz, plagioclase and alkali feldspar. So, and then it depends on the composition. We can have an alkali granite, a granodiorite, or a tonalite. Or if our rock is very quartz rich, then we are talking about a quartz rich granitoid rock. So in the lower part we have the silica undersaturated rocks with more fluid bearing minerals inside, yeah, like the nepheline or the leucite, yeah. That is our fluids which we are having here. So, and if we are going now through all the numbers here, number 1 we have a quartz cyanide, number 2 we have a quartz monzonite, number 3 we have a quartz monzodiorite, number 4 we have then the quartz diorite. So going now to the line below, number 5 we have a cyanide, yeah, we have only a little bit quartz in the system because we are coming here very close to the borderline to the silica undersaturated rocks, and from here to here the quartz concentration increases. Then we have number 6 the monzonite, number 7 the monzodiorite, and number 8 we have the diorite with a mafic with more than 35 or up to 35% of mafic minerals inside. We have here the gabbro, yeah, that is the field of the gabbros here, which contains plagioclase and clinopyroxene. Then we have here also the anorthosite, yeah, at number 8, which contains more than 90% of plagioclase, and the norite, which contains plagioclase and orthopyroxene. Yeah, these are the silica undersaturated rocks. Number 9 we have then the fluid bearing cyanide. Number 10 we have the fluid bearing monzonite. Number 11 we have the fluid bearing monzogabbro or monzodiorite. whereas number 12 we have the phoid-bearing gabbro-norite, number 13 we have the phoid cyanide, number 14 the phoid monzocyanide, number 15 the phoid monzodiorite, monzogabbro, number 16 the phoid diorite gabbro, number 17 the phoidolite, which contains then a lot of nepheline and leucite, and therefore we have then also rocks which we are calling nephelinite or leucites. So in this classification scheme is used for the plutonic rocks. That is the so-called QAPF classification, which I have also shown you last year in our mineralogy class. So now going just to the next slide. Here we have another diagram for the classification of the volcanic rocks. On the x-axis we have the silica concentration, whereas on the y-axis we have the sodium plus the potassium concentration. So and then we have this field inside with these dashed borderlines, and that is the so-called Lemaitre's classification of volcanic rocks. So here we have, for example, the basalts, and here we have the basaltic andesites, dacites, rhyolite. Yeah, here we have this dark shaded field that is the Bader rocks. Yeah, these are these typical rocks which you can find in subduction zones. Yeah, here from silica undersaturated to silica saturated, they can form just by differentiation, fractionation from our originally ultramafic or mafic melt. Then we have here the phonolites, the phonolytic nephelinites, the phonolytic tephrites, the benmorites, the mugerites, the trachyandesites, the hawaiites, the basanites, and the nephelinites. So now we have this is just, I have shown you a few different classification diagrams. Of course, there are a lot of other classification diagrams around, yeah. But we must now not go through all this classification diagram. It is just for you to show that they are existing. So now we will continue with the phase relationship in simple systems, and that is the key to the magma generation, crystallization, and mixing. So I mean, we have now splitted the igneous class and the metamorphic class into the petrology of igneous and metamorphic rocks, which is in year number 4, which is a third year class, and in the fourth year class we have the petrogenesis of the igneous and the metamorphic rocks. So and in the fourth year class, in the petrogenesis class, I will give them a more detailed class where you use different methods to figure out in which geotectonic setting this and that metamorphic or igneous rock is formed. Here we are making now just the simple systems in igneous and metamorphic systems, so that we can pick them, or we can use all this then to build up our fourth year class. And I would be very happy if I can have you guys in the fourth year again. So we are using pressure and temperature diagrams. Yes, that is the most common thing in igneous and metamorphic petrology. The pressure is also an indicator for the depth at which certain minerals are formed. And we have here, for example, the stability fields for the graphite and the diamond. So for the diamond in the pressure and temperature space. So we are starting here. It's a little bit confusing because the author of this book starts always with the low pressure at the top and goes then down with depth to the high pressure variations. And you know, the graphite and diamond, that is a polymorph mineral. So and therefore we have a polymorph reaction from graphite and diamond, and that is pressure and temperature dependent. So and therefore we have here on this line, we have a phase boundary. When we are crossing this line from the upper part into the lower part, we are forming from our graphite a diamond. Yes? So, and that means, depending when we are talking in terms of Gibbs free energy, under this pressure and temperature conditions, we have here a lower Gibbs free energy as here. Yeah? So, and here we have a Gibbs free energy. The Gibbs free energy here at this line is the same. Yeah? So, exactly on this line, we could have graphite and diamond together, theoretically. So here we have the other diagram on the x-axis. We have here the solution series between firelight and forsterite. You know the forsterite, that is the Mg2SiO4 olivine, whereas the firelight is the Fe2SiO4 olivine. And here we have the free energy in kilojoule per mole. That is the free energy. That is the Gibbs free energy. So, and here we have the mechanical solution from between forsterite and firelight. And here we have the ideal solid solution series, and that is, I mean, when we are talking about observation in nature, or if we are doing our experiment, then here we have the ideal solution that is under perfect conditions. When we are changing the mole fraction between iron and magnesium here, yeah? So and then around this line we have then the change depending between iron and magnesium, that is the FM exchange, and here the behavior of the free energy. So, and here we have a mechanical mixture, and the mechanical mixture, that is just a straight line. Here we have another diagram. You know this diagram by now as well. At the upper part we have the phase rule. Yeah, I will now not introduce to you again the phase rule, because we have done this just last semester. We have here the phase diagram of kyanite, andalusite and silimanite. So, and these are the three alumosilicate polymorphs. That means the mineral chemistry is always the same. It's Al2, SiO5. But we are changing the internal structures or the crystal symmetry. So then we have here the point I, which is the invariant point, or the triple point, where all the three minerals are coexisting. So, and here along this line we have a univariant line, and along this line we have one degree of freedom, because we are giving in we will get at a certain pressure a certain temperature. So when we can change here the temperature, when we are using the temperature as an input, then we are getting the regarding pressure along this line, or along this line, or along this line. You know this by now from last semester, where we have done the calculation for the triple point of the alumosilicates, but I think I have done it with the fourth year students. So you guys will do this the next semester. So here the same, this phase diagram you know by now as well. We have a phase diagram for the unary system silica. Silica is also a polymorph mineral, but here we have then the pressure on the x-axis and the temperature on the y-axis. You know that depends always on the order who has plotted the diagram. There is nothing wrong. I prefer always to have the temperature on the x-axis and the pressure on the y-axis, starting with the low pressure at the bottom and getting then higher pressures to the top. But everybody can use it as everybody wants, so there's nothing wrong with it, yeah? So, and here we have then the SiO2 polymorphs. So at low temperatures and low pressures, we have the alpha quartz. Increasing the temperature, then we are forming a beta quartz. Increasing the pressure, then we are forming a coesite. And finally, at very high pressures, we are forming a stishovite. So because that I have told you also already as well, if we are increasing the pressure, then the volume will decrease for one atomic unit cell, and therefore we a rearrangement of our tetrahedrons will take place. So, and therefore the density of one unit cell will rise up. The density of one unit cell will rise up, and the volume becomes smaller for a given mass. So, and if you are increasing the temperature, then the volume will decrease, you know, will increase, yeah, that is like in the system water. When we are heating up the water, then we are forming steam, and the volume will increase dramatically. So, and we are increasing also the entropy, and that is the order disorder from a phase. So these are kind of diagrams you know by now as well. These are the so-called banana diagrams, yeah. So we have here at the top, we have here such a banana diagram for the olivine, yeah. There's percentage forsterite written. That means we have on the right hand of the diagram, we have a pure firelight. And on the left hand, we have a pure forsterite, and we have the percentage of firelight, sorry, yeah. So we are from left to the right, our olivine becomes always more rich in iron, and the temperature condition when this olivine is formed will decrease, yeah. So we have here on the y-axis the temperature, and here we have 100% MgSiO2 crystal, yeah, an olivine, forsterite 90 maybe. No, it would be then a little bit less. Here we have 100%. Formed at 1890 degrees Celsius. So, and here we have our equilibrium. Here we have melt in this phase, this field, yeah, there's just melt. Here, if you are going down here on that point, to that point, we have we have made a complete FM exchange with our olivine. So, and then we have here then forming here a Forster firelight at much lower temperature, around 1200 degrees Celsius. So here inside the banana we have a field consisting of melt and crystals, that is a mush, yeah. So we have a melt, and then these crystals becoming formed out from this melt. So that means and these crystals becoming then removed from the melt, yeah. So, and that means our melt will also always change the bulk chemical composition, because when we are forming a lot of olivines, then we are extracting from our melt a lot of magnesium, yeah. So then our melt the residual melt becomes then also always more and more more and more magnesium depleted, because all the magnesium is picked up by our olivine crystal. And the olivine crystals, they are having a higher density compared to the melt, and then they will just sink down to the ground of a magma chamber, for example. So, and then they are becoming removed of a melt. So, and there is another element which also become enriched in the in the olivine, and that is the element nickel, because the typical mantle olivine has about 3000 ppm of nickel inside. So now we are forming here the first crystals, yeah. Going from here we are going down. I don't know what this is now. Here we are going down, we are going there, and then we are going up to there, and here we have our final crystals, yeah. Here we have our final crystals. Here we have melt and crystals, and here we have then a solid rock. So, and here we have in the number B, we have the lever rule. We have two components, X and Z. So here we have the percentage of liquid, and we are having here, and then we have here this formula to calculate the ratio here between liquid and solid, yeah, that is liquid and solid. So, and if you are going down and down and down here, and here as well, then we have at the beginning we have more liquid, and at the end we have more solid, yeah, and that varies between X and Z. Number C shows us then a temperature melt diagram. Here on that side we have 100% of melt here. While we are cooling down with the temperature, then the percentage of melt will always become less and less and less, and the percentage of solid becomes always more and more and more, yeah? So, and I mean, you know this by now, certain minerals formed at a certain temperature and pressure conditions. So, in an olivine is a pure phosphorid olivine or a magnesium-rich olivine will be formed at high temperatures, and then it becomes removed from the melt. Then when we are forming plagioclases afterwards, then the calcium-rich plagioclase will removed at the beginning, and then our plagioclases becoming also always more and more enriched in sodium, yeah. So, and that is an effect of fractional and fractional crystallization process in such a magma chamber, or also in an experiment. And the reason why the olivine is sinking down, for example, or the plagioclase will float up, that is then the gravity differentiation, yeah. Minerals which are heavier than the surrounding melt will sink down to the ground, and other minerals which are more showing a lower density compared to the surrounding melt will float up at the top of the magma chamber. So here we have here we have again the same diagram, the fractional crystallization of a liquid in the forsterite firelight system. Yeah, that was just this what I have shown you by now. So we have here point BC, there we are going down with our temperature. For example, you can also use this point. That depends just on the chemical composition of the bulk, yeah. So we have a melt with a certain concentration of iron and magnesium inside. If we have more magnesium or another chemical composition of the bulk, then we will start maybe here, yeah. So, but now we have such a bulk composition, yeah, BC for bulk composition, then our melt will cool down. We are reaching this point of the liquid pass, coming to this point, making a solid olivine then, and then we are going down and down finally to this part, and the magnesium iron ratio in this olivine here is then the same as here at this original part. So, but while we are cooling down the melt or along the liquid path, then we are changing always the magnesium iron ratio in this melt, because here we have removed already this olivine crystal. So then we are coming here, going there, and we are forming here the next olivine crystals, which are then already more iron rich. Do you understand this? Yes, I think so. So, and here we have a nice plagioclase crystal, which shows us a very nice zonation, yeah, that is now under the microscope, yeah. Here we have a huge plagioclase crystal, and here you can see there we can observe a very nice zonation here from core to the rim, yeah. So, and here we have now sketch maps. We have a normal zonation. We have here a higher anorthite composition in the center. That means when we have a higher anorthite composition in the center, that means this plagioclase was formed at higher temperatures. Then here we have an anorthite component from 56 inside. That means we have less calcium, more sodium. Then that means this rim was formed at lower temperatures. And here we have even less calcium in our anorthite and more sodium. That means we are decreasing continuously the temperature. So now in our next sketch map we have a reversed zoning. That means we have at the center we have 50% anorthite, that means 50% then albite, and our rim is more sodium rich compared to the center, and that means our plagioclase was heated up. So the melt which is formed before the plagioclase in the center was cooler than those afterwards. So we had then maybe an injection from a more hot melt in a more cooler magma chamber. And then the other one, very on the right hand, we have an oscillatory zonation. There we have the variation between anorthite 60 and 80 goes always up and down, up and down. Then we have here more injection phases maybe, yeah. So, and we as a petrologist, we have to study all these features. You can then measure with a microprobe zonation from core to the rim. And from core to the rim, and then we have to find out the history, the formation history of this plagioclase. So here, for example, we have another nice diagram. We have here A and B, and here number A, we have a mixing of melts number 1 and 2 in the olivine system. X1 and X2 are olivine crystals in equilibrium with melts 1 and 2. That is here and here, X1 and X2, we have a melt crystallizing going there. So, and here we have a melt 2 which becomes heated up. That means we have a mixed melt. So, and here we have in number B, we have a sketch map between the olivine crystal formed by melt 1 and an olivine crystal formed by melt 2. So, and then we are forming mixtures. So and then we have also a zonation in our olivine crystal. So we have now a mixed melt. We have in one melt we can have relicts. It depends which way we are going around. we have a relic of crystal X1 as an inclusion or inside a crystal of the X of the mixed melt. So that means of the mixed melt XM, that is the mixed melt. We have two melts, then these two melts becoming mixed up. So and in melt 1 we have already crystallized an olivine, and in the melt 2 we have also already crystallized an olivine. So and then we are getting here mixtures. We have on the left hand on this diagram we have a relic of the crystal X1 in this composition of the mixed melt. Yeah, then we have here a higher XMG inside the olivine crystal. So and here we have a relic in the mixed melt of X2, and then the rim of our new crystal consisting of the mixed melt composition has a higher XMG. So what we have here, that is we have here at the top a diagram where we are comparing olivines in a lersolite xenolite, yeah. So and then we are comparing these olivines in ingenous xenolites. So I mean, for example, an olivine in a lersolite xenolite, you can find them here, for example, in the kimberlites, yeah. So and then lersolite nodules you can also find in volcanic rocks, depending always under which pressure and temperature conditions these lersolites are formed. So and then on this stack diagram here on the right hand we have the olivine in the ingenous xenolites, yeah. So and they are showing a lower XMG, whereas the olivine crystals in a lersolite are showing a higher XMG. So and that is just also a temperature depending thing, because the olivines in lersolites are formed at higher temperature conditions. So in the olivines in the lersolites, these are olivines which are residues, or which are in the residual melt. So and then you can see here we have a part of the banana diagram. So here we have the olivines in the residual melt, yeah, that you have a magma, then olivines started to crystallize, and then they will sink to the bottom of the chamber, and therefore they formed very at the beginning, showing a higher XMG because they are formed at higher temperatures, whereas the olivine in magmas, they are formed then at lower temperatures, and therefore they are showing a lower XMG. So here we have another nice diagram. On the y-axis again the temperature, on the x-axis the composition between diopside and anorthite, yeah. Here we have diopside, and the diopside, you know this by now, that is an clinopyroxene with the mineral end member composition CaMgSi2O6, whereas the anorthite, that is Ca2Al2Si2O8. So and that is a plagioclase. So and now we are having a melt, and out from that is here in this upper part, there we have melt, and out from this melt we are crystallizing now a diopside and an anorthite. So if we are lying here more on the aluminium rich side of the melt, we are forming here anodosite. Then here when we are more on the magnesium rich side, then we are forming then the diopside. So and here we have the eutectic point. The eutectic point that is here, you know this by now, that is the point where congruent melting takes place. So and therefore we are crystallizing then two minerals at this point, and that is the diopside and the anorthite. So here we have diopside plus liquid, here we have anorthite plus liquid. We are cooling down with our melt, following the path, and here when we are going down here, we are following our path, going here, and here we have then the formation of our anorthite, which shows the same ratio between sodium and calcium as our originally melt. Or we are heating our solid rock up, then we are going from here to there, and then we are making this kind of melt. So now on our the diagram on the right hand, we have here on the eutectic melting, yes, here that is the degree of melting, here the temperature. So and that is at the eutectic point at 1280 degrees Celsius, and then we are making more and more melt, yeah. So and if you are going just up here, then we are increasing the temperature. So and then we are talking about the non-eutectic melting. That is then just maybe here along this curve, yeah. We are going here up from 1280, that is this line here, and we are going then up till 1380. That could be then here, that is probably here, yeah. Where is my mouse? That is here. So and then from here to here we have a non-eutectic melting, and otherwise here exactly at this point we have an eutectic melting. We are keeping the temperature constant, and more solid becomes then liquid. So what we have here at the upper part, we have again a temperature, wise a small fraction of diopside in the diopside anorthite system. I showed you this before as well, that is between clinopyroxene and plagioclase. So and then we are talking here about, we have here different curves. Here we have again the eutectic point at 1280 degrees Celsius. So and here we have the experimental melting curves, yeah. Here we have 100% anorthite, and here we have 100% diopside. And here we have the same melting curve in a gyroscopic system, or calculated using the gyroscopic equation, and those drawn from the actual experimental data. So there is always a difference between our melting curves. I mean, here we have just using the experimental data, and then here at the upper part they have used the gyroscopic equation that you can figure out by yourself. That is just a theoretical calculation how it should melt, and then we have there always differences. And these differences is always that when we are doing some experiments, we are always trying to make it as perfect as possible, but there are always some variation inside. As shown here, we have the activity of the anorthite melt. here in the dashed line, that is the ideal solution, how it should be. So, and that is actually that what we are getting then from our different experimental and gyroscopic calculations. Yeah, I showed you this in the diagram before as well. So, and that is in nature as well. We are never dealing with complete ideal solution. Yeah, we have always some influences or some factors which are modifying the melt curves under ideal conditions. So here we have number A, we have an enthalpy composition diagram for a hypothetical binary eutectic system between A and B. That means here we have a mineral A, here we have a mineral B, or let us better say we are dealing with two phases A and B. Yeah? So, and then we have here the enthalpy that is on this side. We have discussed last semester what the enthalpy is. So, and now we have this for this hypothetical eutectic system. We have here the eutecticum, yeah. So, and if we are increasing the temperature here on these hypothetical dashed lines, then we are increasing the enthalpy, yeah. So, and here we have again the lever rule, yeah. So we have then solid and here we have liquid. Yes, and here we are going then along these curves into liquid from solid, yeah. So, and then we have here again our level rule between 1 and E. So, and if we are moving more and more to that side, then we are forming more and more solid out from our liquid. Or we are heating up our system, or if we are heating up the system, then we are forming more and more liquid out from our solid. That is actually everything what these diagrams are telling you, yeah? So, and if we are keeping the temperature constant at a eutectic point at 1500 degrees, then our melt fraction will increase, keeping the constant, keeping the temperature constant, as well and the enthalpy will also increase with the increasing mole fracture. Going again down to our melt diagrams, here again in the system diopside and anortite, we are going here down with our melt to our eutectic point. And that is our liquid path, and here we will then start crystallize. When we are going from the lower temperature into the higher temperature, then we will, that is here the solid path. So, and we can go from the higher temperature down to the lower temperature here, and crystallizing here minerals out from the melt. So that means our melt fraction becomes here higher and higher if you are going that side. So, and the ratio will always change here between 1 and 0 at the eutectic point, because we will continue while we are cooling down with the formation of more and more crystals. So now we have here another nice diagram, also between diopside and anorthite, and you can observe a lot of this of thermodynamic things already in thin section. So here we have a photomicrograph showing granophyre texture, also called eutectic and eutectoid texture in a granophyre. Yeah? So that means we have here these whitish crystals. This is then the plagioclase, and here these dark ones. This is the diopside, and that is a so-called symplectite texture, and that you are getting here at this point, yeah? So because there at this eutectic point you are forming these two crystals. So and in the figure below we have the liquidus and the solidus curves here. Here we have on the x-axis again the temperature. Here we have on the x-axis we have the pressure. Here on the y-axis the temperature. Here we have some modification. Beta, gamma, yes. And here between these two curves, the liquidus and the solidus curve, we have a crystal mush. Yeah, we have melt and crystal. So and then it depends on the temperature and pressure conditions. Our liquidus and solidus curves will also, or the liquidus and the solidus will also be different, and the formation of the minerals out of the melt afterwards is also different, as well as their crystal symmetry. Here we have another diagram. In diagram A we have the temperature from ranging between 1050 and 1500 degrees Celsius in the system between nepheline and SiO2. So, and you know, here on this side we are silica saturated, on this side we are silica undersaturated. So, and you know by now that you can either have a silica saturated rock or a silica undersaturated rock. So we have discussed before now the things what happens on the eutectic point, yeah? You can crystallize these two minerals. Now we are discussing what happens on this boundary between silica saturation and silica undersaturation. We have here this diagram, Si2 saturation on the right hand, SiO2 undersaturation on the left hand. So if you are going now very back to the class today, I showed you the QAPF diagram, and there at the upper part of the QAPF diagram you have the silica saturated rocks, and on the lower part of the QAPF diagram you have the silica undersaturated rocks. So and there exactly at this boundary between the two triangles, I mean in the upper part you have a triangle, and in the lower part you have another triangle, but this triangle is upside down, yeah? So and there you have this thermal boundary. So and on the right hand of the thermal boundary we are forming silica, we are sitting in a silica saturated system, and here, and here on the left hand of the thermal boundary we are sitting in the silica undersaturated system, yeah? So and when we have a melt, if we have a melt and we are coming directly to this point here, then we can either go there or either we can go there. But here we will not go there to form a mixture between a silica saturated or undersaturated. We have either a silica saturated or either a silica undersaturated rock, like here in B. Here in B we have just this inset. Here we have melt number 2 following this way, and we are forming here at the eutectic point a rock containing nepheline and albite, yeah? Having a melt composition M1 going from that to that side, going down to the eutectic point here, and forming a rock which contains the minerals albite tridymite, and tridymite, that is a high temperature quartz modification, and we are sitting in the silica saturated system. Yes, that is what's happened at the thermal maximum or thermal boundary. We have the thermal boundary, and at this thermal boundary we can have silica saturation, or we are forming silica undersaturated rocks. So, and now we are going to the next phenomena. We are talking now about the peridactic point, yeah? So, and that we have now discussed the eutectic point, we have discussed the thermal boundary. Now we are talking about the peridactic point, and that is point number P. That is the peritectic point, and such a peritectic point we have in the system forsterite SiO2. Here we have the forsterite, which is an olivine, and it is the olivine is a mineral occurs in silica undersaturated rocks, yeah. In silica undersaturated rocks, it's Mg2SiO4. Then we are adding to the olivine SiO2. Then we are forming an enstatite, which is an orthopyroxene with the mineral chemical composition Mg2Si2O6, and then we are going very to the right hand on our diagram. We are having then SiO2. So here at the peritectic point, we are going down here on the melt curve, solid, liquid, solid curve. Here we have a mixture between solid and liquid. Going down to the peritectic point, we have this situation. We have incongruent melting, yeah? At the eutectic point, we are talking about congruent melting. We have a phase, a solid phase, and from this solid phase, we are making a liquid phase. At the peritectic point, we have incongruent melting. That means we have an enstatite crystal, for example, then we are forming forsterite plus liquid, and this liquid is then, in this liquid you have SiO2, and then we are forming an enstatite. So now we are going to side, and then finally we are going down to the peritectic point. So now we are having here number B, equilibrium crystal of OTH. At first we have to find out what is OTH. That is the equilibrium crystallization of a liquid OTH. So now we have here at the point OTH, that is, we are sitting here in the liquid, going down along this curve containing here liquid plus forsterite, going down here to the peridotite, to the peritecticum, where incongruent melting will take place. Then we will form, if we have this melt composition, we are going down here, and here we are forming then a rock containing forsterite and enstatite. If we have more silica in the system, we are going down here, going immediately down here to the eutectic point, and we are forming here a rock containing enstatite plus cristobalite. And cristobalite, that is also a high temperature modification of SiO2 of quartz, yeah? Or you can go down here. We have a solid rock containing a lot of forsterite cooling down. Now a melt, and here we are going down. We are coming from here this way from the pass, and then cooling down, forming the rock and forming also this forsterite plus enstatite bearing rock. But in this example we have this equilibrium crystallization of OTH, of a melt composition, which is here represented by OTH. So here we have the equilibrium crystallization of a starting liquid TH is shown. So we are going here down again, coming here to the liquid melt curve, going here down to the peritectic point where incongruent melting takes place. We are starting with a temperature at 1580 degrees Celsius, where we start to crystallize forsterite rich olivine crystals. So, and here when we are going down from TH to this curve at point number R, there we are, our melt TH reaches the liquidus. So, and the corresponding forsterite crystal formed are at the point Q, that the point Q is here. So, and as we are cooling down, our melt follows the path RP, P is the peritecticum, and then to the eutecticum. So, and if we are starting with this melt composition, it goes then down here, and then we are forming an enstatite plus cristobalite rich rock. Yes, because our original melt composition has more silica inside, as in the example before. So, and that is now here this crystallization curve. We are starting here going down at from 1580 degrees Celsius. Here we have the percentage of crystals which we are forming. We are forming here forsterite, and we have here having here forsterite plus liquid, and forming enstatite, and we have enstatite from our melt plus liquid, and here we are forming then at the end enstatite plus cristobalite crystals at the end. And these crystals from the beginning, they had already have been removed from our melt, sitting now in a residual rock. So now we have here 3 new diagrams. We have the fractional crystallization of OTH, starting here at very high temperatures, and the melt will follow following the part A. The melt will following the part A, PE. Yes, we go down here A, PE. While the solid path will go here, and that is from here to here. So then we have here fractional, that was fractional crystallization. Here we have the opposite case, we are increasing the temperature. We have now fractional melting of X. So, and there the path will then go the other way around. We have here the rock with composition X here. We will heat this up. So, and then we are following the following path. We are going from N to T T apostrophe, and then that is here T apostrophe. Then we are going from T apostrophe here to T, and then to TP, and then we have here a pure forsterite melting at point TP. So, and now number the next diagram here. We have here a melt mixing. Here we have melt 1. Here we have melt 2. So, and then we have here 2 melts, and we are mixing up these 2 melts, and then we are getting a new melt composition like here. Yes, you can have 2 melts. You can mix up vanilla pudding with choco pudding, and then you are mixing them up. And then you are getting a new chemical composition or a new bulk composition. Yeah. So we are subdividing fractional crystallization with from fractional melting and from melt mixing. Yeah. That would also be a nice question for the examination. So here we have now these melt banana diagrams in the plagioclase K-feldspar system. Here on the left hand we have sodium Al Si3O8, that is the albite, and on the right hand we have the potassium Al Si3O8, that is on the albite was on the left hand, and on the right hand we have the K-feldspar with the chemical composition potassium aluminium Si3O8. So, and now we have here between the mixture of the two feldspars, yeah, going here up or down. It depends from which side you are coming, from the lower temperature into the higher temperature, or from the higher temperature to the lower temperature. We have here a single feldspar at certain temperature condition. We can have a mixture of both feldspar. For example, when we are going down with the temperature, yeah, we are coming in this field with the single feldspar SS. That means solid solution. Yeah, we are going down to this point. Then you can form here at the solvus, you can form here the K-feldspar, and here you can form the sodium-rich albite. Yeah, we have here the miscibility gap, and there we have the two feldspars inside. Here we have a single feldspar. If we are going up with the temperature above 1080 degrees Celsius, yeah, then we are forming then at the upper part liquid. Here we have liquid, and here we have Lewisite plus liquid. And here on the right hand and on the left hand we have two melt bananas. Yeah, here we have for the melt banana for the alkali feldspars, and here we have Lewisite plus liquid, and here we have Lewisite plus feldspar plus liquid. So that looks then in under the microscope. Like here we have a photomicrograph of a peartite, and that means here we have when we are talking about a peartite, we are talking about we have exsolution, partitic exsolution lamellas, and that means before we had a melt with the chemical composition of one feldspar. We are cooling them down, so and then we are forming partitic exsolution lamellas in an feldspar. So, and here we have then the part, extinguished part is the hosting feldspar, yeah, that is the dark part, and these whitish parts, these are the plagioclase exsolution lamellas in this pertite. So pertite means we have a hosting feldspar and we have exsolution of plagioclase inside. So then we can have forming an antipertite. That means we have a plagioclase hosting mineral and we have then exsolution lamellas of K-feldspar inside. Here we have the regarding PT diagram, the temperature composition diagram, yeah, albeit autoclass. So, and here we are forming then here this exsolution lamellas in this hosting feldspar. And here we have the two feldspar plus the vapor. So we have here the sodium feldspar plus liquid, K feldspar plus liquid. So we are going down with our curve. So and then at this point we have a liquid with the chemical composition of 1 feldspar, and if we are cooling this down very, very fast, then we do not have time for any crystallization. So and therefore we are getting then such a high temperature feldspar, which is a mixture from both. So, but if crystallization takes place and we are following down our curves, then we are getting then exsolution from one mineral in the other mineral, yeah? So now we are going back to the system for sterile water. We have here on the y-axis again the temperature. Here we have sterile plus vapor. And here we are increasing the pressure. So, and water has a very high influence of the melting behavior of certain minerals and also rocks, of course, then. If we have more water inside the system, then our rock starts at lower temperature to melt, yeah? If our rock is more dry, then our rock starts to melt at higher temperature. If there is absolutely nothing inside, then our rock can remain metastable under pressure and temperature conditions which they are not supposed to be at home. So, and therefore we are moving then around with the eutectic points. Here we have melt number 1, here we have melt number 2, yeah? And the melting point from melt number 1 is a different temperature compared to the melt from number 2. So, because here we are adding now here is the dependence of the pressure. Here we are talking about 1 gigapascal, and at 1 gigapascal we have here the eutectic point here at point X, that is the water concentration. It will melt just at 1920 degrees Celsius, whereas here we are going then up with the temperature when we are dealing with higher pressures here. But the X water is still the same. So if we are increasing the pressure in our system, then melt will take place, or melting will take place at higher temperature, yeah? So, and this is the same for the water. If we have more water available, then we can decrease the temperature, and if we have less water available, then we are increasing the temperature. So, and that is seen in diagram number B. We have here the curve for a volatile free solution. So, and then the melting points, and here we have the pressure, and here we have the temperature. So, and here we have the water saturated solidus. We are dealing with much lower temperatures, as at the volatile free solidus. Yeah. So what is important now for you as a third year beginner student in engineers petrology, the important thing here is now the important thing is now that melting occurs is not only a temperature dependent thing, it is also strongly dependent on the pressure and temperature, on the pressure and volatile concentration in our system. So here we have figure number A. We have the bulk rock composition, BR, yeah, that is bulk rock here. Here we have a eutectic point, here we have the liquid. So, and here we have the dependence on the pressure, yeah. So, and if you are increasing the pressure from 0.0001 gigapascal over 1 gigapascal to 2 gigapascal, then our eutectic points will move along the system, bulk rock system between A and B. At 1 gigapascal, the eutectic point will exactly be at the same place where our bulk rock composition is. So at higher pressures, at 20 gigapascal, our eutectic point will much more move to the side of the bulk rock of mineral B. Herrgott nochmal. Whereas at very, very low pressures, it will be more on the bulk of mineral or rock number A. So, and with increasing pressure, we are also increasing the temperature. Can you see this, yeah? So then at diagram number B, we have the calculated PD diagram for the bulk rock. So we have here the pressure on the x-axis and the temperature on the y-axis. And you can see here we have the line between eutectic point 2, eutectic point 1 over eutectic point 2 to eutectic point 3. Here we have liquid 1, liquid 2, liquid 3. We have mineral composition A plus liquid here, mineral composition B plus liquid here, and here we have liquid. So it's strongly dependent on the pressure and temperature conditions where congruent melting takes place, and congruent melting happens on the eutectic point. So, and now we have added here the pressure, yeah? We have here temperature and pressure variation, how it will vary and how it will affect the melting behavior of a rock. So now we are going to the figure below. We have then now the effect of water. So, and that is the phase relationship between diopside and anorthite. So, and here we have a eutectic point number E2. We have a highly aluminous melt, yeah, because we have the phase relationship between diopside and anorthite, and the anorthite has aluminium inside, whereas in the diopside we do not have aluminium inside. So, and if you have more aluminium in the bulk inside, then we can form more anorthite crystals, whereas if we have less and less or no aluminium in the bulk inside, we will form not only one plagioclase crystal, because there is no aluminium available, yeah? So, and here we are moving to a higher temperature than our here we have a pressure of, here we have water pressure, that is now the influence of water, so the water pressure of 1 gigapascal. We are going down with our we have here and 1 gigapascal, we have here an eutectic point number 2 at lower temperatures. Then we have here an eutectic point at 1 bar. We have here more water in the system. Then here where is less water, we are at 1 bar, we have the eutectic point much more on the diopside side and at higher temperature. So that means the pH2O lowers the solidus and the liquidus and significantly changing the eutectic melt composition. So that is now the water pressure in a system, yeah? And that will lower the eutectic point of a melt composition. So going now to the next slide. Yes. So here we have at the upper part, we have here again pressure dependent diagrams of different melt systems. Here we are dealing in melt systems at the upper part between silica undersaturated and silica saturated. Seen here on that side we have the enstatite, on that side we have the quartz. Here we are dealing here at the upper diagram at a pressure of 1 bar, that is the atmosphere, yes. Then below we have then 0.13 gigapascal. And then at 2 gigapascal our diagram looks totally different. So at atmospheric pressure, here we have our classical diagram. Here we have a peritectic point and here we have a eutectic point. Increasing the pressure, we do not have here a peritectic point anymore, it's just the eutectic point between the silica undersaturated and the silica saturated rock. Now increasing the pressure dramatically, then we have here a thermal boundary. Yeah? We discussed this earlier today in class, the thermal boundary. We can go either to that side or either to that side, reaching here, this eutectic point on the silica saturated side, or this eutectic point on the silica undersaturated side. So, and that is now really a lot of stuff for you, but the relationships behind are very, very easy. Yeah? That is just how you are moving around while you are increasing your pressure, temperature conditions, as well as the water conditions of our system. So here we have this diagram more in detail at a water pressure of 2 gigapascal, and then we are lowering the system again. Yeah, that was without water, showing the thermal boundary. Here eutectic point 1, here eutectic point 2. Now we are adding a water pressure to our system. Then we have here our peritectic point, that is T, a temperature condition at the peritectic point. Here we are going down, we are having our eutectic point, yeah. So here we have now our more silica saturated rocks, and here we have forming our silica undersaturated rocks. So how does this look like now in a ternary system? So we have here a ternary system between 3 minerals, for example, or composition A, B, and C. So, and here on this line we have eutectic point 2. Here you have the eutectic point 1. In these diagrams before I showed you always one surface, yeah? One surface, that is this surface, that was one surface. Then here we have another surface, and here we have another surface. So we can split every ternary system here in 3 binary systems, yeah? And here in this ternary system we can then form, we have 3 compositions, yeah, I mean we have 3 minerals, so and therefore we have then the variation of 3 binary systems showing always the composition between 2 minerals, yeah. So that means here between mineral A and B on this surface, that means the mineral A and B on this surface, or along this line is between mineral A and C, and along this line is between mineral A and C and B. So now we are dealing here with higher temperatures going down on our liquid solidus curve to the peritecticum, to the eutecticum, and here on that side the same, cooling down, cooling down. Here the same, we are cooling down, coming to the eutectic point, and here the same, and here the same, and here the same. And that is then here shown very much more easier, starting with the melting temperature of component C going down. Then we are going down here, and we are going down there. Here we have now component B will cool down here. You can see it on the curves here, yeah? And here the same. And here the same. And then you are forming here again a new eutectic point, where you have then the mixture of 3 minerals, yeah? So we have now here, for example, plotting the ternary composition in a triangle. Yes, for example, for the plagioclases, yeah, we have component A, B, and C. So, and then we have here along this line, you know this now, how you can plot minerals in a ternary, in a diagram. We have done this last semester, but here just to repeat the whole thing. So, and here along this line, for example, you are getting minerals containing only compositions between A and C, whereas in the triangle you are plotting minerals showing the composition between A, B, and C. So therefore we are using these ternary diagrams. We can show 3 compositions always. So, and here we have now in A, on that side, we have the equilibrium crystallization starting with the starting melt. And the starting melt we are calling M. So then we have the liquid passes from M over to eutectic point number 1, number 2, and number 3, that is here. Here we have the eutectic point at 1470 degree, 1490 degree, 1560 degrees Celsius at E2 between the composition of A and B. So and now we are going along the solid path from B over 2 apostrophe, 3 apostrophe, 4 apostrophe to M. So what is important for you now, we have here 3 eutectic systems between 3 components. We can construct here a binary diagram with a eutectic point. Here and there we are cooling down this 3 composition. We have here eutectic point number 1, eutectic point number 2, eutectic point number 3. And here we have finally a eutectic system between this 3 binary system at 1320 degrees Celsius. So here, for example, we have a diagram number B. We have here the temperature on the x-axis and the melt fraction on the y-axis. So, and here we are starting at 1300 degrees Celsius. We have liquid plus B plus A plus C. Then here we have then at higher temperatures we have only liquid plus B plus A, because C is already now disappeared and is in the melt. That is this component here, yeah. And then finally we have here at higher temperature, like of 1400 degrees Celsius, we have then only liquid plus B, because A and C has disappeared and already in the melt. If we are following this from our starting melt composition at M, yeah. So here we have now number A, we have equilibrium melting of a composition X in the system ABC, yeah. Number B, we have fractional crystallization. And number C, we have fractional melting. So, and therefore we are following always other passes, yeah. So, and you can always go in both directions. You can go from here down, yeah, to the eutectic point, or you can go the other way around, yeah. You can start here with a starting mix and heating this then up. Or we have here a starting mix of such a melt composition and cooling it down, yeah. At 1600 degrees Celsius, you are cooling it down and following your path from the other side. So, or at fractional crystallization, we have here this melt mix. We are going from here to here and here to the eutectic point in this 3-dimension figure, yeah. Or we are going here from fractional melting directly to point 2 from the eutectic to the solid top here of eutectic point number 3. So this diagram is then more important for us. So because here we have a ternary system, again with here with eutectic point number 1, eutectic point number C, eutectic point number 3. And between the 3 minerals or phases A, B, C. So, and here we have now a cross section through from X to Y along different temperatures, crossing here the eutectic point in the middle. So here we have now the pseudo-binary diagram between X and Y. So, and here we have the composition, we have the solid rock between A, B, and C. That is at this point here. That is this point is now shown here. And here we have the different eutectic system between here and there, yeah, because here we made a cross section, yeah. So then we have only the involvement of phase B and phase A here in the upper part. And here we are passing it by here. So, and here we have then AC plus liquid on this side. Yes, that is from here to here, AC plus liquid. On this side we have BC plus liquid, that is here. Here you have the points F, yeah? Increasing the temperature. Here this curve, these two, between these two curves, you have this field here between, yeah? So here we are having ranging with the temperature, depending where we are here, along these dashed lines. So, and here we have then A plus C plus liquid on that side, yeah, within this field. And here we have at point A, that is point A. Here we have point B, that is at point B. And here when we are going from this jump from here to here, then we are moving here to this curve finally. And that is here then for point A, that is then here. Here that is point X from here to here. Here we have point B from here to here. And here we have point C. So the same for this side. Here we have point D from here to here, that is from here to here. Then we have point E, that is from here to here. Then we have point F, that is from here to here. And here we have point Y, that is from here to here. Yeah? And here in this upper field, we have then only liquid, yeah? So, and that is now this pseudo-binary diagram for this cross-section between X and Y. You could also make it like here, or I could make it like here, that doesn't matter. So, and that is the reason why we are using this triangle system, just to get some clarity when our rock will melt. So here in the upper diagram we have now a diopside on the top. Sorry for that, it's cutted that way. But you have then the PowerPoints also on Moodle where you can download it. So in the part below you have the anortite and the forsterite system. Then you are getting here different phase fields. You have here anortite plus liquid. You have here forsterite plus liquid. Here you have spinel plus liquid. Here you have your eutectic point. And here you have diopside plus liquid. Yeah. So now you are cooling down, going from here to this point. And here you are forming then finally your solid rock. So how does this look like in the next figure? We have here now a quaternary system, yeah, using a tetrahedron. We have here diopside on the top. Here we have anortite, forsterite, and silica. So and then in the upper diagram, I have just shown you this surface, yeah, between forsterite is here, anortite is here. Here at the top is diopside. I have just shown you this surface. If we are using a quaternary system, we can add one component more. And here we have then added silica. So, and then you can have here again the next system between forsterite, silica, and diopside. If you are using the diagram in the back, then you have anortite, diopside plus silica. If you are using the diagram below, you have silica, forsterite, and diopside, silica, forsterite, and anortite, yeah? And therefore, you can use such a quaternary system for showing all the phase relationships, possible phase relationships between here, for example, diopside, silica, forsterite, anortite, and enstatite. Yeah, and you have then here also the pigeonite inside, which is a calcium-rich orthopyroxene. Then you have here the protoenstatite and therefore we are using the system. And normally we are just going for the ternary system, because if you are using then this quaternary system, then it becomes maybe for some people too difficult, yeah. So that's the same again. So now we are having the next diagram, figure for the melt relation between diopside, albite and anortite is shown on the figure above. Here at the top we have again the diopside at high temperatures at 1350 degrees Celsius is shown here in the dashed line. Here we have the anortite 1500, 1550 degrees Celsius. Here we have the albite, which is formed at much lower temperature. Here we have two eutectic points, E1 and E2. So that means here we have this mixture of the plagioclase crystals, yeah, and here we have the diopside inside, and here we are starting, for example, with the melt composition of A, like you have seen in all these diagrams in the binary system, in these composition diagrams in the binary system before. We are going here down with the temperature here, we are going down with the temperature here, and coming together at this eutectic line between eutectic point 1 and eutectic point E. If we have a more anortite rich, or if we have a more calcium rich melt, we form then anortite plagioclase at higher temperatures. And our eutectic point is then also located at higher temperatures, as in the system where we are dealing with a more sodium-rich plagioclase, and our eutectic melt is located at lower temperatures. Number B, we have now again the system diopside, albite, anortite, and we have a liquid pass and a total solid pass. So here along this one, that is the red line, that is our liquid pass. Yes, starting at the composition of A, we are going from here to here, we are cooling down, and then we are coming here to this black line, and we getting here then finally our solid rock out. So, and here we have now in the inset B the three-phase triangle at 1223 degrees Celsius. We are going down this side in the ternary system, and then we are going here to the more albite rich side, and we are forming then from our more liquid or liquid rich more rock then the solid rock finally. Here we have again the system albite, diopside, anortite, diopside, anortite, albite with different curves, and here we have then different points. We are starting here with different anortite composition. Here we have an anortite with 50% calcium, 60% calcium, 70% calcium, 80% calcium, 90% calcium. So, and that depends, gives then different results when we have a different bulk rock composition, yeah? So, because then we are changing our melting behaviors and our melting temperatures here between E1 and E2. and that is strongly dependent on the bulk rock composition, yeah? So our melting behavior is now dependent on the melting behavior is now dependent on the pressure conditions, on the temperature conditions, on the water conditions, as well as on the bulk rock composition of our bulk rock, if we are heating it up and that it becomes to melt, or if we are cooling it down, then of course the whole resulting rock type strongly depends on the bulk rock chemical composition of our melt. So here we have again the variation between anorthite and albite here just on this surface. So and then we are getting here then different results. Here we are starting with a melt composition O, then we are getting here our eutectic point at lower temperature because the albite plagioclase is formed at lower temperature. But you can then read by yourself the text below. But for you now as a third year student, it's important to understand how these diagrams in principle working and how or what are the factors are to influence a melt. It's the pressure, the temperature, the volatile concentration and the bulk rock of our melt, or if we are producing melt from an existing rock sample, from the bulk rock chemistry of our rock. So now we have this one again, diopside, forsterite, silica, a new diagram with new phase relationships. So if we are going more to the silica saturated side here, we have then just two liquids, and forsterite and diopside crystallizing at higher temperature. Then we have here forsterite plus melt, and here we have protoenstatite plus liquid, and here we are bringing in the diopside, here the pigeonite, the autoenstatite, and the protoenstatite. Here you have the different temperature lines, yeah, 1557, 1543, and here the other temperature relationship when we are going more to the calcium-rich side to form a diopside. So here we have now just an expanded view of the portion of the system, diopside, forsterite, silica. That is just this view here, yeah. Here we are going to the more silica-rich side. Here we have our pigeonite, yeah. Here the enstatite, and it would be a good exercise for you if you are comparing all these diagrams with each other, that you are getting a three-dimensional idea how they are fitting together, yeah? How these diagrams fitting together, because here you are just showing again the peritectic point, which you can see on these melt diagrams in the system between forsterite and silica. So and here at between you are forming then on the more silica-rich side you have enstatite plus SiO2 at the end, and here you have forsterite plus SiO2 plus enstatite at the end, yeah. Therefore, it is also important, if you are just using triangles, plotting different mineral composition inside, and then you finally will get it, and you are following always with your melt along these proposed or suggested passes in these diagrams. So here, for example, we have again a part of the triangle forsterite diopside silica. So and here we have then just very close to the forsterite, to the forsterite. If you are going here more to the silica rich side, we are getting here the protoenstatite, here the pigeonite, here the protoenstatite plus the pigeonite. Here we have forsterite plus protoenstatite plus liquid. Here when we are going here to the more calcium rich side, we are getting then the diopside inside. So we have here the three-phase triangles for forsterite, protoenstatite and olivine. Then we have forsterite, protoenstatite plus P1, that is the peritectic point 1, that is here. Or we have forsterite, pigeonite plus 1, that is here, are shown to construct a liquid path. So and it depends also strongly again on the bulk composition, on the pressure and temperature relationship, which liquid passes you are following in your example. So here, for example, we have the triangle between anorthite, forsterite and silica. We have here forsterite plus liquid, here we have the silica, here we have anorthite plus liquid. So and here we have the pressure at 1 atmosphere, that is 1 bar, and here that is shown in dashed lines. 1 gigapascal is shown here in the solid lines. So and then you can see how our curves moving with increasing or decreasing pressure, yeah? So and here between we have our eutectic points, and they are of course moving then also with increasing pressure, yeah? Or decreasing pressure. It depends always from which side you are coming. Then we have here again the diop on the right hand. We have the diopside, silica, forsterite. We are dealing here with the curve at number B at 1640 degrees Celsius at a pressure of 2 gigapascal for a dry rock composition. So then we have here the same. We have here a water pressure of 2 gigapascal, and then we are going already down here to 1220 degrees Celsius when we have a lot of water inside, and here we have the dry composition, yeah? And then we have here we have 420 degrees Celsius, a difference of 420 degrees Celsius. Then here at the pressure at the atmosphere, that means at the surface, 1 bar, we have here temperatures of 1386 degrees Celsius in this system for a given bulk rock composition. So, and that shows again how strong the influence of water is under silica saturated, under water saturated conditions and dry conditions. So here in this figure on the right, on the left hand, we have a triangle connecting coexisting liquid forsterite and clinopyroxene. Diop-solid solution is used to determine the direction liquid movement of up and cooling on the boundary. Forsterite plus diopside plus liquid. So here we have our liquidus curve, yeah, and between the dashed line between enstatite and diopside. So, and here we have now our diopside in solid solution. So, and now you can go from this side of the path and you are heating it up, or you are going down. So when we are forming then, we have here the cooling curve on the boundary curve, and we having then the constellation forsterite plus diopside plus liquid. Going to the triangle on the right hand between forsterite, silica and enstatite. Then we have again here the binary system, which I have shown you today a lot of times at the beginning, yeah, between forsterite and silica, the enstatite between. Then we have here on this side the system between forsterite and diopside. And here we have the liquid, and here we have the silica. So when we are getting in this triangle the different mineral assemblages plus their liquids. And here we have the maximum temperature. So here another nice diagram. Here the temperature on the x-axis, the pressure on the y-axis in the system with carbonates. We have now put in carbonates. Yeah, carbonates are playing also an important role there in our melt system, because it's not only water which is important for melting rocks or in the crystallization. It is also the CO2, and the CO2 in bounded form can be found in the carbonates. Yeah, we have here the magnesite inside, we have the dolomite inside. Yes, and then we have here the thick line. Here we have a carbonate melt, and here we have silica melts. Yeah, carbonate melts, and here we have silicate melts, and here we have the solidus. And here the phase relationship, yes, we are forsterite, enstatite plus diopside plus vapor cooling down. Then we are getting here CO2 in the system, and this CO2 will then result in the formation of dolomite and at higher pressure in magnesite. So here we have now added the CO2 as a component, SiO2, CaO, magnesium oxide. And then when we are adding CO2 as a component, we are getting then also the carbonate-bearing minerals. So, but the CO2 is CO2 itself, it is together with water, it forms a very important volatile, which has then also very important influence in the crystallization and formation of melt and rocks. So now diagrams number A, B. What do we have here? We have now at diagram number A, we have the system silica, calcium oxide, magnesium oxide, yeah. And therefore we with calcium oxide here, we are bringing then we have a CMS system, and we are adding then CO2 to the system. So, and then we can form then also minerals like dolomite, which is seen here, yeah. We have here enstatite, forsterite, enstatite, dolomite. Here we have the diopside, and here we have the maximum temperature for all these three rocks together. That is shown in the curve forsterite, enstatite, liquid. So, and in this number B, we have then the different melting curves and solid solution curves for the system, including the CO2. I just read through. That is a CMS ternary diagram at 3 gigapascal projected from CO2, yeah. There you are using a quaternary system because it is projected from CO2, that means then to the fourth point. So, and here we have the projection from CO2 into this system, and therefore we have these four curves. And at 3 gigapascal, I mean the curve at the left hand, that was the same system, but for 2 gigapascal. Comparing it now to 3 gigapascal, it looks like totally different. So again, you can see here how strong the fluid or the volatiles are affecting the melting relationship in certain rock system, yeah. Here in the mineral in the triangle on the left side below, we have now added to the magnesium, silica and calcium, we have here added the fourth component in the quaternary system, CO2. So, and then we can now make a new projection. We have here the CMS space. That is the CMS space. That is this one here. That is the CMS space. And here we are adding the CO2, and that we are making. So we are going now from a ternary system, from the CMS space into the quaternary system. And then we can make this projection through CO2. In the 3 space, we are going there, getting the mineral composition here, liquid 2, liquid 1, somewhere inside in our quaternary system, yeah? And this we can then project through these lines into the CMS space in front. So that is now a little bit complicated, but it doesn't matter. Just it can actually all be seen very easily only by showing the geometric relationships in all these different figures. So we have here now on the right lower side, we have a new diagram constructed near solidus to near liquidus temperature at 3 gigapascal in the system forsterite, diopside, enstatite, CO2. So, and here we have now the oxide weight percent, yeah. Here we have the oxide weight percent, we have here more silica rich composition, then we are magnesium rich, more calcium rich, CO2 rich. And we have here on the x-axis the temperature. And then we have here our different solidus liquidus lines, which are crossing here at this point, and this point forms then a eutectic point. When we are going down here from the higher temperatures into the lower temperatures, then we are forming here, then starting to form here a solid rock. Which is shown here again, yeah? Here we have now some questions. Yes, here we have now some questions. Problem 1. And here we have this one, that is problem 2. And here you have problem 3. And I will copy this together for your next test, yeah? As an exercise, and then you can go through all of them. And, there then you can go through all of them and answering it. And some of these problems or exercises I will then also use for the examination. That is problem 1. Yes, that is then also for the exam for the test. You should try to answer problem number 1 now. Moment. You should try to answer problem number 1, and you should answer answer the question of problem number 2, and you should answer the question of problem number 3. So, and now we have here the next question. Which you should then also know that is a sketch. You have here again the I think that depends to problem number 1. Let me just check in the book. Hello. Yes, we are at the end for today, yeah? We are at the end for today, and you should then just try to answer or make the exercises for problem number 1. That is starting here at problem number 1. Then here you have, I do not know what's going on now. I just don't know it. Here we have starting with problem number 1. Then you are doing the exercises, problem number 2, problem number 3. So in problem number 3 depends to this figure, yeah. The problem is the sequence of the scans is not complete, is not in the right order, but you should do the exercises for problem number 1, problem number 2, problem number 3, and should hand it in, that you can then, there you have a while time, you can hand this then in maybe in 2 weeks time. So okay, then we are at the end for today. We are in a good time order. We have now just covered a huge part already from the ingenious stuff, yeah. I will load up the PowerPoints, what we have done additionally also on Moodle now. And I will also upload then these exercises, but by now you are busy with the question which I have handed out to you last week or at the beginning of this week, which you should then hand in by the end of this month. So we will continue next week with our class, or maybe I will upload something during the weekend, I don't know. We will probably have one ingenious 3-hour class more, or maybe another 4 hours. Then we will do our metamorphic stuff, and I think we will be done till the 25th of September with this class, with the theoretical part. Then we will continue with this examination preparation, where I will give you then test number, the next test, which includes then a lot of these exercises here, and this will also result in some questions in the text, in the examinations. Okay, then thank you for listening, and see you then later on.